The nickel-cadmium battery is a small light and is made in a sealed unit. It is used in portable appliances such as calculators and electric razors. The following two half reactions occur, and they give you the half reactions and they write them in the right order nicely for you. So you can quite clearly see where your oxidation is and where your reduction is. So which half reaction occurs at the anode? Give a reason for your answer. So we need to consider what happens at the anode. The anode is where electrons are lost. So we are going to land up with reaction number 1, which is this substance over here. And what is my product? My product is electrons. So that's where electrons are lost. So anode is oxidation, and oxidation is loss of electrons. So you can give those all as reasons. So it's reaction number 1, because reaction number 1 loses electrons, and loss of electrons is oxidation. Oxidation occurs at the anode. All of that. Which substance undergoes oxidation? So it's obviously going to be, let's do our little oxidation numbers, 0, and over here this turns into +2. So it is the cadmium itself that undergoes the oxidation, where its oxidation state goes from 0 to +2. Derive an ionic equation for the overall reaction for the discharging process. In other words, when it's giving me energy. In other words, when it is spontaneous. And that's exactly what they've set up for me here. So I'm going to rule a line. I'm going to put 2 over there so I balance the number of electrons. 2, 2, 2, 2, and write it all out. So it's cadmium on the left, plus 2 OHs on the left, plus 2 nickel oxide, hydroxide on the left, plus 2 H2O, all on the left. Going to the right, we've got CdOH, 2, plus 2 NiOH, 2, plus 2 OH minuses, and the good news is I can cancel those 2 OH minuses on either side, and obviously I could have cancelled the 2 electrons, which I did as I was going along. Now, using your result obtained, state in which direction the cell reaction would proceed, forward or reverse, when the cell is being charged. Now, charging the reaction is exactly opposite. I put electrical energy in to reverse this chemical reaction. So what is going to happen is I will have the reverse reaction going when it's being charged, and the voltage of the cell remains at a constant 1,35 volts. And why is that? Well, it's either on or off. And this half cell will have a fixed E0, and this half cell will have a fixed E0. I don't know what the values are, but those are fixed values as long as the cell is operating under standard conditions. So a standard cell has that. It's got an anode that is given to me and a cathode that I have to now work out. So is the cell an electrochemical or an electrolytic cell? Why? You haven't done electrolytic cells yet, but you're going to. An electrolytic cell is when I put energy in. An electrochemical cell is when I get voltage out. This one gives me a voltage. In other words, I get energy out. It is giving me a potential difference. It is a spontaneous reaction, which is an electrochemical cell. In which direction will the electrons flow in a conductor which links the electrodes? Well, aluminium has been given to us beautifully here. Its aluminium goes to Al3 plus 3 electrons. That is quite clearly an oxidation. If it's an oxidation, that means that the electrons must flow from the aluminium, because here those electrons are, they need to go somewhere, towards the other metal, which I do not know. It is metal 2 plus, which is going to obviously then gain 2 electrons and become metal. So in which direction do the electrons flow? From the aluminium to the metal. Write the net balanced equation for the cell reaction. And so if I'm going to write the net balanced equation, I need to sort out these electrons. I've got 3 here, so I'm going to go 2, 2, 6, 3, 6, 3. And I land up with 2 aluminiums plus 3 M2 pluses gives me 2 Al3 pluses and 3 metal. Calculate the reduction potential of that particular electrode. Well, I know that aluminium, if I take a look at the redox table, is minus 1,66. But here it has changed its sign. Why? Because I wrote it backwards, so it's plus 1,66. I know my answer overall has to be 1,53. So what is this x? And the x turns out to be equal to negative 0,13 volts. So therefore, what is M? It must be lead. An electrochemical cell is set up under standard conditions with magnesium as the anode of the cell and an unknown metal X as the cathode. A voltmeter is connected across the terminals of the cell and has an EMF of 3,17 volts. A bulb is marked whatever, 3 volts, 6 watts. And so now I can ask electricity questions if I wanted to. They won't go into much depth because it is the chemistry paper, but they can expect you to at least know watts is power, volts is potential difference. Is connected in parallel across the voltmeter, but the switch is open, so it actually means nothing yet. Give the values of the standard conditions that apply to the cell, and it's going to be 25 degrees centigrade, and then you've got Mg2 plus is aqueous, and it's operating at 1 mole per cubic decimeter, and the X, I don't know whether it's X2 plus or whatever. I'm just going to go with plus, because I can. I don't know what it's going to turn out to be, and they can't expect me to know yet, so I could have said anything as long as I've said it's 1 mole per cubic decimeter. So those are my standard conditions. There are no gases here, so I don't talk about 1 atmosphere. Identify metal X by using my standard electrode potentials, show all my working. So the first thing is, I've got magnesium here, and magnesium is going to magnesium 2 plus 2 electrons, and X is doing the other thing. I've just written magnesium backwards. If I write it backwards, I change its sign to 2,37. Now I have got an answer over here. So I do know that I've got 3,17 as the answer. So what is the X? The X must turn out to be equal to 0,8 volts. Now 0,8 volts belongs to the silver ion. So only metal that has a potential difference of 0,8 volts. So identify it. It's silver. Write down the cell notation for the entire electrochemical cell. So let's do that. We're going to start. We're going to say my anode is magnesium, going to magnesium 2 plus. I put a salt bridge. Oh, sorry, that was a bit more than a salt bridge. I put in a salt bridge, and I then say that the silver plus becomes silver metal. Write down a balanced overall equation. I now need to multiply the silver by 2. So it's Mg plus 2Ag plus becomes Mg2 plus Ag. And then when the switch is closed, the reading on the voltmeter drops to 1,5. Why? Think back and remember that whenever you used to have a battery and a voltmeter, that was me measuring the EMF. The minute I put a circuit onto that, I have what's called internal resistance. So there's going to then be internal resistance. And that is the factor that is responsible for the dropping of that potential difference.